welcome back to this week's Mathcast podcast. Today we're going to be talking about the fascinating topic of numbers. Now, this is a podcast episode that I've been wanting to do for quite a while, and I just wanted to get together all my thoughts, everything I wanted to say about this topic, which may, just from a standpoint, seem extremely simple and straightforward, where the numbers are just 1, 2, 3, 4, 5, and so on. But there is so much more to it than that, and so I'll be talking about the types of numbers that there are. So it isn't just the natural numbers, which we know as 1, 2, 3, 4, and 5, and so on, all the way up to infinity. But there are also so many different types of numbers, so I'll be talking and covering that. I'll also be talking about the number 0, which is a number that is not very much appreciated as much as it should be. And I'll just be covering how the number 0 became a number, because a lot of times, and I'll get into this a little bit more later, but hundreds of years ago, mathematicians refused to accept 0 as being a number. And just to start off, I'll talk about the story of how numbers as a whole were invented, because a lot of the times when we think of mathematics as a whole, we normally think of numbers or formula or whatever comes to mind. Normally, numbers has, to some extent, something to do with that. So numbers actually weren't invented the way that you would think, like on a chalkboard where people wanted to invent algebra or geometry or whatever else, but it was actually caused because of sheep. Yes, you may be replaying it right now just to check that I actually said sheep, but yes, it's sheep. Now, how this came to be is that there was a shepherd, and back in this time, people would use to let go of their sheep to wander around in the mountains, and they would collect them back to shear them, gather the milk, and whatever else shepherds do with their sheep. So while they were doing this, a lot of the shepherds had a problem, and this problem was that they didn't know if they had all their sheep. So just imagine the situation, right? You don't know what numbers are. You just are a shepherd with sheep, and you want to know if this is the same amount of sheep that you had at the start. So the shepherd was able to obviously tell quantities, okay? So let's say there was a herd with 100 sheep and a herd with 30 sheep. The shepherd would have been able to tell the difference, because you don't need numbers necessarily to work that out. You can just look at the big sheep and look at the small amount of sheep and just tell that there's difference. But they don't know how much of a difference, and that was sort of where the problem was, because they didn't know if there was 30 sheep and if there was 31 sheep. You wouldn't necessarily be able to tell that just by looking at it, and that was the problem. So then a form of counting or numbers was invented, and this is called a one-to-one correspondence. So what happened is that they paired up each sheep with a stone. Alright, so say right now I've got 30 sheep, but I don't know that there are 30 sheep. And just for the purpose of this, I'll just not know that there are 30 sheep. And these 30 sheep, I'll pair each sheep with a stone, okay? So I'll have 30 stones and I'll have 30 sheep. Then I'll let the sheep wander off in the winter, and then I'll gather them back up in the spring, or whenever they used to gather them up. And then I would pair each stone with the sheep. And if there are any sheep that are missing, then I should have a leftover amount of stones. So say only 28 sheep come back. I'll have 2 stones left over to tell me that there are sheep missing and that sheep haven't come back. And that's how I'll know how to gather my sheep. And this story just fascinates me so much, because it's such an obscure way to introduce numbers into the world. And after this story happened, a form of counting was invented, and this later on developed and became numbers, and then it turned into the base 10 system that we know today. So now we know how numbers were invented, but this is just for countable objects. Now you might start to get where I'm going with this, and I'll go to the topic of the number 0. All right. So as you could see with our sheep example, we were counting things, objects, right? This is a sheep, 1 sheep, 2 sheep, 3 sheep. That I could do, but the idea of having a number 0, well, what's the usefulness of that? Like, people would get that 10, there is a 1 and there is a 0, but they wouldn't get the idea of nothingness. And mathematicians just didn't understand why we would need a nothingness just to appear, because at the time as well, like evolving from the sheep scenario, when numbers were invented, they would mostly be used for trading things or just trading money or whatever else they used it for, but it would be used for some sort of currency. And why would you need to document that someone had no money if just it's not like a transaction that you can make? I gave her 0 sheep, so she gave me 0 cows. Like, that doesn't really make sense. So they didn't understand why the number 0 was invented. And it was first made as a placeholder, a way to tell 1 from 10 and 10 from 100 and so on. And they understood the concept of having 10, 1 and 0, like I said before, but they didn't understand the idea of nothingness. Nothingness just didn't make sense. And still to this day, there is some confusion around the idea of the number 0. Why is it a thing? And that story also, just as well as the sheep scenario, just fascinates me so much, how a number that is so incredibly obvious to us now, like immediately when I think of numbers, I think of 0, 1, 2, 3, 4, 5, and so on. But that number 0 just wasn't a thing back then, and that's just what fascinates me so much. So the number 0 actually has some other, say, problems. And there are things that you can't do with the number 0. So things like dividing by 0. You probably would have thought about this before. Well, why can't I just divide by 0? Just click it on my calculator. But no, even on a calculator it says maths error. And I find that quite interesting, how on a calculator, if you type any number divided by 0, it will give you a maths error. So yeah, you just can't divide by 0. It's always been a bad thing to do. And the funny thing is that even the calculator is taught. It's taught. It doesn't even try to give you a good answer. It's just taught to just give you a maths error when you try dividing by 0. But why is that a case? So we'll start by remembering our sort of primary school definition of division, right? So when you were in primary school and someone would have asked you, what is division? Or when you started learning about division. So it's just repeated subtraction until you reach 0, right? So when it comes to do something like 10 divided by 2, we're just doing 10 minus 2, then 8 minus 2, then 6 minus 2, then 4 minus 2, and so on until we reach 0. And 10 divided by 2 is obviously 5, because it took us 5 times to get to 0. But dividing by 0 is a little bit more complicated because the loop is infinite. The number doesn't get any less. You start with 10, you subtract 0, you get 10. Minus 0, 10. Minus 0, 10. You get where I'm going. No matter how many times you subtract 0, it's still going to be 10. So in that argument, using that argument, 10 divided by 0 is equal to infinity. But it's not that simple. Because if 10 divided by 0 is equal to infinity, then using the same logic, let's say 2 divided by 0 is also equal to infinity. Because you can do 2 minus 0, 2 minus 0, 2 minus 0 forever. And if 10 divided by 0 is equal to infinity, which is then also equal to 2 divided by 0, then that means 10 is equal to 2. And that just destroys the system, which is why the calculator is taught to just give you a math error, and why it is a bad thing to do. Because we get nonsense things such as 1 is equal to 2, or 10 is equal to 2, or just all numbers are going to be equal if we use this way, because anything divided by 0 is going to take forever to solve, which means that it's equal to infinity. And this is just one way of approaching this question, and this is a way that we already see the consequences of doing, because we already know that it's impossible that 1 is equal to 2, because that just doesn't work. Now, another way to approach it is by looking to values which are really, 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 really close to 0. For example, 0.1. Then we can keep on getting closer to 0 and we see the pattern. We see where it approaches. So for example, say we do 5 divided by 0.1. And that is equal to 50. We can see that the answer is getting larger, right? 50 is obviously bigger than 5. But we can do a little bit better. We can get a little bit more accurate. So let's see what happens when we divide by 0.0001. Now 5 divided by 0.0001 is equal to 5 followed by 4 zeros. And when we get even more close to 0, if we do 5 divided by 0.000000000, you sort of get the idea, right? Just put a 1 at the end. It's going to be equal to something really, really large. 5 followed by however many zeros we put. And the numbers get really big and really, really fast. However, this only goes to show that the closer you get to 0, the larger the numbers get, tending towards infinity. We cannot say for certain that it's going to be equal to infinity, because infinity is just a concept, right? It's not a number. It's not something that we can show. That's why it's called infinity, because numbers go on forever. You can always keep on adding 1. But like what I said before, this can't just be the case, because it leads to things like 10 is equal to 2. And another point to add is that we've only tried this approach to approach 0 from the positive side. So we've done going from the number 1 towards 0, so doing things like 0.000001. That's from the positive side, but we haven't tried it from the negative side, because remember, numbers aren't just positive, they aren't just natural numbers. There is also a whole other side of the scale. So the thing is, when you try to do it with negative numbers and you do 5 divided by negative 0.1, you get your answers tending towards negative infinity. And I find that so fascinating that when you approach 0 from two infinitely different sides, you get 2 completely different answers. So when you approach it from the negative side, you get negative infinity, and when you approach it from the positive side, it's tending towards positive infinity. And you just get 2 infinitely opposite answers. See what I did there? Infinitely opposite. And therefore always dividing by 0 will always result in a maths error. And there are other things which are banned as well. Things like doing 0 to the power of 0. Now, unlike dividing by 0, doing 0 to the power of 0 leads to the same answer of 1, no matter which way you approach it, whether that be the negative side or the positive side. If you try to approach it from the positive side, you are tending towards 1. If you try to approach it from the negative side, it gives you an answer of 1. But it still leads to a math error when you type it into your calculator. But why? And the reason for this is that you need to still approach it from the complex numbers. And complex numbers are something that I'm going to get into a little bit further into this podcast. But pretty much it's the square root of negative 1, okay? Which is represented by I, which is a number, and you represent the square root of negative 1 as I. And it's, as you may have noticed, it's called an imaginary number because it's not a real number. It's not something that you can actually do. Square rooting a negative number doesn't work, because any negative number, when you multiply it by itself, you always get a positive number. So negative 2 times negative 2, 4. And so on. If you multiply any negative number by itself, you will always get a positive number. And a better name for the imaginary numbers are called complex numbers. And because they are used to solve perfectly real things. So if we go back to 0 to the power of 0, when we approach it from the complex plane, for which we have to draw a whole new axis to our 2D number line, we get different limits that aren't 1. And that causes another math error. So, as you may have noticed from my rambling on about 0, 0 is a very complicated number, but that doesn't mean that it has to be ignored. Doesn't mean it has to be removed, as mathematicians did before, which is why we currently have the number 0, and it is a placeholder, but it is also the number that separates negative and positive numbers. And the cool thing about 0 is that it has its own sort of category. Neither belongs in the negative numbers, which is the whole right side of the number line, 1, 2, 3, 4, and so on, all the way until infinity. Nor does it belong in the negative side, negative 1, negative 2, negative 3, negative 4, so on, all the way up to infinity. But it's sort of doing its own thing. It's just there. But it's a great number, and it's useful for so many different things. But there are a lot of things that you can't do with 0, like I discussed before. Things dividing by 0, doing 0 to the power of 0. It's just mathematically not possible yet. So now I'll move on to types of numbers. So far I've talked about the origin of numbers, number 0, and now I'll talk about the types of numbers. So I'm pretty sure I started with this podcast by saying that we are familiar with the numbers 1, 2, 3, 4, and so on, all the way up to infinity. And we are also familiar with the numbers -1, -2, -3, -4, so on. But these numbers have also got names. So we've got the natural numbers. And the natural numbers are the numbers that we learned first. 1, 2, 3, 4, so on, to infinity. We've also got a whole new set called the whole numbers. And it is the same as the natural numbers, 1, 2, 3, 4, and so on. But it also includes 0. Moving on, we've got the integers, which are the same set of numbers again, but it includes negative numbers. Then we've got the rationals, which are any numbers that can be written as a fraction. Because so far, integers and natural numbers aren't fractions. I mean, they can be written as fractions. They are a rational number, technically, because 1 can be written as 1/1, which is a fraction. Therefore, it's a rational number. But it has its own category. It's a natural number. 1 is a natural number. And it is also an integer. And it is also a rational number. So we're getting progressively further away from the origin. So for example, I started with natural numbers. Natural numbers are natural numbers, but they are also integers, which are also rationals. But integers aren't necessarily all natural numbers. But all natural numbers are integers. Hopefully that makes sense. So then we've got rational numbers, which are just decimals, fractions, anything that can be represented as a fraction. And the opposite of rational numbers is irrational numbers. And irrational numbers are things like that we are already familiar with. Things like pi. Pi is an irrational number because its digits go on forever. And there are no repetitions. It doesn't repeat, and it cannot be written as a fraction. Now, some of you might say, well, pi is just the circumference divided by the diameter. That's a fraction, but it has to be a number, like a number fraction that can be used. For example, 2.5 is 5 divided by 2. That is a rational number, and that is not an irrational number because it can be written as a fraction. Therefore, it's a rational number. Then we've got the real numbers are pi, e, which is also an irrational number, but it is still a real number because it is something that can be made, something that you can do. Negative pi is a real number, but these numbers are also transcendental. The difference between them is that all transcendental numbers are irrational, but not all irrational numbers are transcendental. Then we've got the complex numbers, and these are numbers that are so hard to understand. They are also called imaginary numbers. You need to imagine them. Even though you just can't imagine the square root of -1, you can imagine what that looks like, which is why it's called an imaginary number. But a better name mathematicians like to use is complex numbers, because imaginary numbers, I'm pretty sure I said this before, is they can be used to solve perfectly real things. And they are used to, they are denoted by the letter I. If you do a lowercase I, that is an imaginary number. So that's pretty much all for this podcast. We've covered the topic of numbers from start to finish. Start with the sheep and finish with who knows how much more there is to numbers. But that is all for this podcast. Thank you so much, and I hope you enjoyed listening.